Thanks. Yeah, I've worked for Washington State University since 1984, and I've been based at the Puyallup Research and Extension Center. And one of the kind of the long-term focuses of our work has been what I call organic nutrient management. And so that includes animal manure, it includes compost, it includes biosolids, it includes a whole lot of other products that sometimes the greater world considers waste, but that has an agronomic value. And we've done nitrogen management work, a little bit of phosphorus work. In more recent years, we've been looking at long-term effects on soil quality, and have also since about 2000 now, been doing work with organic farming systems. So this mostly focused on small-scale vegetable production, but they are, users of some of these organic materials that we've been studying for years. I did do some work in Whatcom County back in the 1990s. I may seem like a stranger, but to the old-timers, they probably remember us hauling up here. I'm with Dan Sullivan, who's now at Oregon State University, and Andy Berry, who's still with me. And we did some nitrogen management. We had some funding back around 95, 96, 97, and I'll allude to that a little bit in the course of the talk. But with that, we'll begin. The focus today is on soil testing and how that affects nutrient management. There's a number of different types of soil tests we can think about. The one that we most commonly associate with soil testing is testing for nutrients. And that's where I'm going to focus today. Soil quality testing, a lot of this is what we can do ourselves. The texture of the soil, the structure of the soil, the compaction of the soil. We don't have to send the sample out to the lab. We can use our own senses to get an understanding of that on our farm. Contaminants are rarely an issue unless you live in the shadow of a smelter or an old apple orchard or something like that, and that's not the case in the situation we're talking about today. And biological soil testing is something that maybe the past 10 years or so we've seen a little bit more of, but at this point biological tests do not have the research base to connect them really soundly with management decisions. So it's not something that I recommend. So we're going to be focusing on the nutrient testing. If we think about nutrient management, we know a key goal is to meet crop nutrient needs. That's pretty obvious. But there's some other goals that we sometimes don't think about as much, but they're there. A second one is to maintain soil quality. And certainly one advantage in a system where you're using animal manure, we're getting that organic matter into the soil, and that's going to provide soil quality benefits. Better tilth, better infiltration, better drainage. If you're sitting in a wet spot, the drainage isn't going to get much better from organic matter, any better, but in other soils you can get some benefits there. Conserve resources. This not only includes our natural resources, but it includes the resources that sit in our wallets. We don't want to spend more money on nutrients than we need to. And then finally, and this is an important one, and I think one that in Whatcom County everyone is keenly aware of, is protecting water quality, reducing leaching risk, and reducing runoff risk. And I teach a lot of master gardener classes, and what I like to tell the master gardeners is although this seems daunting to try to meet the crop nutrient needs and not go overboard, this is not like walking on a tightrope. It's more like driving down the road and trying to stay out of the ditch. So we need to be, getting kind of feedback from the environment around us. Yeah, I'm on the road, I'm driving down the road. We can't fall asleep at the wheel, but otherwise, we have means to kind of stay within those boundaries. So there's nothing particularly exotic about nutrient management. Just a brief introduction. We know that plants require 13 different nutrients. We divide them into two groups, the major nutrients, the micronutrients. The ones that are in blue are ones that can be deficient in western Washington soils. The one in red, the nitrogen, that's the one that is most frequently deficient, but also the one that can most easily get us into trouble because we have a lot of nitrogen to deal with, and we can over-apply nitrogen. It can have negative effects on crops, and we know that excess nitrogen can leach into groundwater. So I'm going to spend, when I talk about nutrients today, a big focus on nitrogen today, also some focus on phosphorus, and then focus on soil testing and a couple other things like pH as well. If we think about nutrients in soil, soil is made up of mineral matter that was derived ultimately from rocks. Here in Whatcom County, they've been moved by glaciers. They've been moved by meltwater from glaciers, deposited by wind, subsequent stream flooding in the post-glacial period, some volcanic ash influence. And those rocks are a vast storehouse of nutrients. You'll find calcium, potassium, phosphorus, iron, manganese. Every nutrient that plants need except for nitrogen are in the mineral matter of the soil. The organic fraction, since this is the decomposed remains of plants, animals, microorganisms, this contains everything essential to life. So the organic matter contains all of the soil nutrients. But in these forms, in the mineral matter, in those sand, silt, and clay particles, in the organic matter, which is predominantly humus, and that humus and some other complex molecules, those nutrients are not available to plants. So we have a vast storehouse of unavailable nutrients in the soil. And what we have to rely on are natural processes, chemical weathering processes to release the mineral nutrients into soluble, available forms. We call these ions. You can think of them as bite-sized chunks. They can be taken up by the roots as the roots take up water. From the organic matter, it's a biological mineralization process that is sensitive to the temperature and the moisture in the soil. The good news is that plants are also sensitive to temperature and moisture in the soil. And the optimum conditions for plant growth and uptake of nutrients mirrors the optimum conditions for the release of nutrients from the soil. So there's a certain natural synchrony there. If we just think about manure for a minute, it is predominantly an organic material. We add it to the soil, and we're adding a slow-release source of nutrients. Now, it gets released a lot faster than does from the organic matter, and if you're putting on manure liquids, we already have a lot of available nutrients there already. But there's some additional that's going to be slow release. Over time, when we add manure, we build up the organic matter pool in the soil, and as a result, we build up the amount of nutrients that are going to be released every year available for crops. And so these historical manure applications actually become a significant source of nutrition for our crops this year. I'm going to focus a little bit on the nitrogen cycle. You know, you may have seen the nitrogen cycle umpteen times before, but it never hurts to look at it one more time because it comes in. It's important for nutrient management. It's important for manure management. As we'll see, it's important in the soil testing world as well. As I mentioned before, the vast majority of the nitrogen is in organic form. This is from soil organic matter, from plant residues, from manure. I took this from a biosolids talk. That's from wastewater treatment plants. There's nitrogen in the biosolids as well. And this is largely unavailable to plants. The only exception is if you're spraying on liquid manure, that has a pretty substantial available part right from the get-go. Now what happens is the biological processes in the soil, as the soil warms up in the spring, the microbes break down that organic matter, and they release ammonium as a waste product. Waste product to the microbes, an available nutrient to the plants. So the plants can start taking up this ammonium. There's other, so let me get that on there. There are other microbes who see this ammonium as an energy source. They're called nitrifiers, and they will take the ammonium, and they need oxygen as well, and they will convert it to nitrate. Both of these are simple soluble ions, both of them available to plants. Now with nitrate, we have a dilemma at the end of the growing season, because the nitrate is very soluble in water. That's why it's available to plants. And also it's not held to the soil particles. So when the winter rains come, the nitrate is going to leach from the soil profile. And if you're over the Sumas Abbotsford Aquifer, it's kind of a non-stop flight down into the groundwater. So that's one of the challenges we face with nitrogen management. Now, if your soil is wet and heavy and the water just seems to stand on it, doesn't really move very far through it, or you have a high water table, so I don't see how that nitrate's going to leach out of it. The water's just sitting there. There's another loss mechanism, which is called denitrification, and it releases nitrogen in gaseous forms. Now, there was a time when we thought, well, denitrification is our friend, because we're taking nitrate that might have leached into groundwater, and we're turning it into nitrogen gas, that N2 there, which comprises 80% of the atmosphere. It's harmless. We've just gone back and kind of, back to the beginning of the nitrogen cycle, as I'll show. But denitrification also releases some nitrous oxide gas, which is a greenhouse gas. So that's one that we have concerns about. So enhancing denitrification is not really a solution to our problem unless we could get all the way, 100% back to nitrogen gas. So these gases go to the atmosphere, and then what I won't go into today is that when you're growing clover out in your pastures, we're going to fix some of that nitrogen from the atmosphere and get it back into the plant residues, which will decompose to organic nitrogen, which then ammonium and nitrate is released. So we have a cycling system here. So when we have legumes, nitrogen fixers, growing clover in a pasture, you're going to be adding nitrogen. If you purchase alfalfa, that is fixed nitrogen that we're adding. If you purchase, say, a grass hay, that is probably nitrogen that had been in fertilizer form originally and is now in the grass. So that's and we're going to get back to that nitrogen cycle when we get into soil testing. The other little just piece of basic science I want to mention right now is soil pH. pH indicates relative acidity or alkalinity of a soil. You see we have the pH scale up there. pH of 7 in the middle is neutral. pH of 6 and lower or below 7 is acid, above 7 is alkaline. Nothing magic about a neutral pH. We don't have to farm in soils of neutral pH. But one important thing to remember is this is a logarithmic scale. That means that it is like a Richter scale for earthquakes. A 1 unit change in pH is a 10-fold change in acidity or alkalinity. So pH 5 is 10 times as acid as pH 6. pH 4 is 100 times as acid as pH 6. Then the same thing is true at the other end of the scale. So why is pH important? There's really 3 reasons. One is it affects the availability of nutrients. So for most crops, in a pH range, say 6 to 7.5 or 5.5 to 7.5, we're in a range where most of the nutrients have a fairly, a reasonable solubility and availability to plants. Phosphorus particularly is more available in this range. As we get to low pHs, phosphorus becomes less available, but iron becomes more available. Blueberry plants, if anybody grows blueberries, and there's a lot of blueberries in this county, they need low pH because they have a high iron requirement. So those soils need low pH. For growing corn, for growing pastures, we want a little bit higher pH, 5.5, 6, 6.5, 7, in that range. pH also affects the availability of toxic metals. I'm specifically right now thinking about aluminum. We worry about various toxins in the environment. Well, the soil contains nearly 10% aluminum. Nearly 10% of the soil's mass is aluminum. And aluminum is toxic to plants. It's toxic to just about everything. So we can ask the question, if soil has so much aluminum in it, why is there life on Earth? What is keeping us alive? And the reason is that aluminum is tied up in the soil. It's tied up in the mineral fraction of the soil in the normal pH range, or say, 6, 7, in that range, and it's unavailable to plants. Its concentration in the soil solution is so low that the plants can tolerate it. When we start getting down into the low 5s, there's enough aluminum there that it's going to start harming the plants. It's going to reduce our yield. It's going to reduce our ability to take up nitrogen, phosphorus, and some of those other nutrients. And when we get down to pH 4, if you're not a blueberry plant, you're not doing much at all. You're probably dead. And at pH 3, we would have a moonscape. And fortunately, the Earth is fairly well buffered, so we don't, seldom see a pH that low. And then pH also affects microbiological activity. The extremes of the pH range, nutrient cycling is slower than it is toward the middle of the range. So what affects pH? One is climate. Humid areas tend to have acid soils. Arid areas tend to have alkaline soils. We generally have acid soils on the west side of the Cascades because we're generally a high rainfall region. If you go over to Squim or onto Whidbey Island, their pH is a little higher than what the rest of us have because they're not quite so humid. Parent material, the rocks from which the soils develop. Some contain lime and keep the pH higher. We don't have too many soils containing lime in western Washington, so that doesn't kind of buffer us very much. And then the third one, and this is an important one, management. Many fertilizers tend to produce acidity. Most nitrogen fertilizers will do that. If you add urea, if you add ammonium sulfate, as the ammonium gets converted into nitrate, you create acidity. If we add organic fertilizers, including manures, the same process happens. So we tend to be moving towards acidity over time with our nitrogen management. It's just an inevitable piece of that. And so what we need to be able to do is to monitor our pH. So that's an important role of soil testing is pH. And then adjust the pH as needed for optimum crop growth. This publication here is hot off the presses or hot onto the web, like within the last week. And this is a bunch of authors on this, and some folks who played with us for a long time remember Dan Sullivan. He's one of the key authors on this out of Oregon State University. Applying lime to raise soil pH for crop production, says Western Oregon. It works for Western Washington as well. It gives pH ranges. It talks about how pH or lime application rates are determined. A lot of information about lime. It also has a special section on if you have a pasture and you're applying lime to the surface where we can't incorporate it. Some guidelines for pasture applications. And basically, the short story is that it says, yeah, if you're below the optimum range for pastures, liming is going to be beneficial. You might not see it the first year. You might have to wait till the second year before you see that benefit. And because we're putting it on the surface and it takes a while to work in, your soil test may come back and tell you to put on 4 tons of lime. Their recommendation is don't put any more than 2 at a time on. You're not going to get benefits beyond that, so you may need to make applications a little more often than you might otherwise, but a couple tons would be the maximum. But anyway, this is the hottest thing on the market for pH, so I You can be the first on your block to get it, so I recommend that one. Yes, Chris.
Steve Franson had recommended or talked about the calcium chloride lime test versus water lime. And the differences in have you had any experience with those?
The pH tests that are done traditionally here in the Northwest are water-based pH tests. But our lime requirement is actually based on another test. It's a buffer test. It's not the same as the calcium chloride one, but it's a buffer test that looks at the reserve acidity of the soil. And you actually use a chemical solution, you measure the pH of the soil in that solution, and it kind of is grabbing some of the acidity out of it. And so it's that buffer test that's used to make the lime requirement. So if you had a sandy soil with a pH of 5 and you had a clay with a pH of 5, it would take a lot more lime to raise the pH of that clay soil than the sandy soil, just because it's more highly buffered, and this test takes that into account. There's been a lot of different approaches over the years, and this is the one that's, it's probably simpler than a lot of the other approaches, and it works just about as well. So.
And that buffer test is called what? It's called buffer test?
Yeah, it's called, sometimes you see the SMP buffer, and it's named after the three guys who devised it. The first guy is Shoemaker, the last guy is Pratt, and the guy in the middle guy, M is for middle, I guess. I can't remember his name. And that will show up on the soil test forms, and I'll show an example of a soil test result in a little bit, and you can see where that shows up. So that's an important one, because manure is not going to be raising our pH, and so it's something we need to be aware of. Oops, where are we going? Okay. So what is a soil nutrient test? Okay, it's a chemical evaluation of the nutrient supply from the soil. So we use something to extract the soil with. We extract some nutrients, and then that tells us something about our nutrient status and our nutrient needs. The reason that soil tests work as well as they do is back in the 1940s, 1950s, 1960s, the way that soil scientists made their living was they would try different soil test solutions. They would extract soils. They would then, from farms all over the place, they would then grow crops on these farms, and they would supply, adequate levels of every nutrient but one, and they would vary the level of those nutrients. And then looking over all the farms, they would see, is there a correlation between that soil test level and how much fertilizer that we needed. So that's how these soil tests were developed. And this is an example, and this is old stuff. This was published in 1972, data from the 1960s, 50-year-old data, some of it, and still showing it today. But what this is this was a phosphorus soil test, and they were looking at winter wheat in western Oregon, and winter wheat's making a comeback again. It was kind of out of favor for a while, but it's making a comeback again. And all these little points are different farms. And what the points are is on the x-axis here along the bottom, that's the phosphorus soil test level. The higher the number, the more phosphorus the soil test was saying was in the soil. And then on the y-axis here, this is the grain yield index, and what that is, that's the ratio of the grain yield of the unfertilized plot with the grain yield of the plot that had the maximum amount of phosphorus applied. And what we see is we can run a curve through all those points. It's not a perfect curve, but you can see that if your soil test is below about 20, and your grain yield index is generally less than 100, in some cases way less than 100, that phosphorus is going to benefit you. You add phosphorus to the soil, it's a benefit. We get up to 20 to 40, and there's a few lower ones and some higher ones, and there the phosphorus might help you, it might not. You get up 40 and above, and if you're buying commercial fertilizer, phosphorus is a waste of money, because it's going to have an inconsequential effect on your yield. So this is how we can use a soil test number to make a recommendation for fertilization. And your question?
Yeah, that curve temperature related.
This would have been done over about 30 farms, or maybe it was 10 farms over 3 years, or 30. Well, actually, it was 30 sites over about 6 or 7 years. So there's not a big temperature relationship there.
Often they say cooler temperatures, less mobile or available, and so you get into discussion about applications when we're starting the plant versus something that becomes more available.
Right. There's the whole, for say row crops in a low to moderate phosphorus soil. Maybe even a medium one where you wouldn't see much response normally. You might be able to get a little starter response from the banding just to improve the root growth in the cold soils. And what's interesting is it's not always it's not always phosphorus that's making the plants a little purple in the cold soils. And I think it's in that new pH bulletin that they talk about that some. I think that's where that is. I was just reading some things on that just the other day. But anyway, this is so they have 6-7 growing seasons there in different field sites, so a pretty broad range, and we see that trend there. So that's just some of the kind of the background of soil testing. When you're going to be soil testing, and I know that a lot of folks, have folks who do the soil testing, so I took out my slides on, how many holes to punch in the ground and what to use and all of that and how to handle a sample. But I will mention you want to make a sampling plan. Obviously, if it's a dairy farm, you're going to have a number of fields and you're probably either growing grass or pasture. So each of those fields would be one management unit for you. If you have a mixed crop farm, it can become a little bit more complex. And so if you're just growing, say, corn and grass, and you've got 4 fields of corn and 4 fields of grass, you have your 8 units, and there's your sampling plan for what you're going to sample. Okay, when to take a sample? You obviously don't want to take it right after you've applied manure or fertilizer. You want to do it before. And I recognize that in a dairy situation, you're applying manure several times a year. There's not maybe a clear-cut time to apply. So a couple times it could work pretty well. One would be in the spring, before you've applied manure. If you've had a window there for a while, that would be a time to take a basic test. And I'll talk about specific nitrogen tests in a little bit. Another time would be in the fall, because a lot of times we do post-harvest nitrate tests in the fall. There's been some gap from the last manure application, and so that could be a time where you could get a 2-for-1. You go out and sample, you have your 12-inch sample for your nitrate test, and you use the same thing for your basic general nutrient test as well. And it depends on how often you soil sample. Some people like to do it every year. Some people are required to do it every year. If so, do it every year. Sometimes we can wait every 2-3 years and kind of let the picture play out a little more and then see, do we have to change our management. Choosing a lab. I think most folks probably have labs that they've been relying on. Just a couple things. Because sometimes, somebody will send us some really funky numbers and we scratch our heads and we don't know what to do with them either. But, the question, does the lab routinely do ag tests? Do they use the standard test methods? And most of the folks around here will either use the Oregon State University ones or the University of Idaho, which were the same as the old WSU methods. WSU hasn't had a lab for 31 years now. I still think that was a bad decision, but we don't have a soil test lab. The Oregon State soil tests work pretty well throughout Western Washington, the Western Oregon ones do. Does the lab give fertilizer recommendations? A lot of them do. I like to take those fertilizer recommendations in one hand and then a production bulletin about the crop that I'm growing, whether it's silage, corn, or whatever, in the other hand, and kind of use both of those to see what we need. You want to know how to send the sample. Do they want it air dried? How much does it cost? How fast is it going to get back? And can I understand the report when it does come back? And if you've been using a lab for years, you're probably in good shape on all of that. But if you're in the market for a lab, those are things to think about. Another thing we sometimes don't think about, but a lot of the well-known soil testing labs do both of these. Quality assurance programs. There are some national proficiency testing programs where a soil test lab there's this kind of this proficiency guru, and he will send out samples to various soil testing labs, the same sample to all the lab, and he's analyzed it 1,000,000 times himself, so he knows kind of where the numbers should come back, and then gets the numbers back and sees, okay, are they in range or not. And then another thing that can be worthwhile, if you only have one field and one sample, submitting a known sample as a check doubles your cost. But if you're sampling, I think most people are going to be, having, say, 6, 8 fields. Because if you have one sample you've collected and archived, and you got a box of this stuff, and every time you send in a sample, or every, say, a set of samples, you include one of those knowns, and then you can see, does it come back where it's supposed to? We have found, and we work with soil test labs, and we work with some of the best labs, but there are times when somebody hits the wrong column on the spreadsheet, and it doesn't multiply something by 2 or by 10, and these numbers come back, and you say, they look really funky, and you say, can you check these? And usually, not always, but usually we can find that there was a problem, and that known sample was what really keyed us to that. If we're looking at soil nutrient tests, if you ask for a basic test, west of the Cascades, I had added electrical conductivity there, it's not there. Oh, west of the Cascades, you get phosphorus, potassium, calcium, magnesium, boron, pH, the lime requirement, that's that SMP Shoemaker, Middle Guy, Pratt buffer test. It tells you how much lime to add. Because of new WSDA requirements, we also need to ask for electrical conductivity, which is routinely done east of the mountains. It's a test for salts. As I'll mention later, guess what? We have a lot of rain, stuff leaches. We don't have salt issues in our soils, or it would be very, very unusual to have that. You can get the Cadillac test that has various micronutrients and organic matter and other things. But generally you don't need most of these. And the question is, if we look at the basic test up here, which nutrient is missing from this basic test that we'd really like?
Nitrogen.
Nitrogen. And I'll talk about how we address nitrogen in a few minutes, because it's critical for us. And the good news is that for dairy management, there has been more work done on nitrogen soil testing than for any other type of agriculture. And so we have a couple of things that we can work. So you might ask, why isn't nitrogen on this basic list? And why, if soil scientists have been, for the last 70 years working on soil testing, why isn't there a good predictive nitrogen test? We can go out, sample the soil, and say, okay, we need so much nitrogen for the next growing season. The reason goes back to a slide I showed very early on when I mentioned the mineral matter of the soil has all the nutrients in it except nitrogen, and the organic matter has nitrogen as well as a lot of the other nutrients. So for nitrogen, the whole show is organic matter, the whole show is biological, and these soil tests are chemical extractants. What we need is a biological test. So as researchers, we can collect soil samples, we can bring them into the lab, and we can incubate them for, 70 days. The equivalent growing degree days of a growing season. We treat them real nice, and we give them moisture, nice warm temperature, kind of like they're spending 70 days in Maui or something. And then we extract the ammonium and nitrate at the end and see how much it's changed. That's expensive. And soil test labs do not want to have to be babysitting thousands of incubations that came in at different times and extracting this up. So they don't do it. there are some simpler tests that sort of work sometimes. This is the holy grail of soil testing. But there's not one that is highly reliable that everybody's taking to the bank. So the basic tests, they just don't do it. And if you're not using, if you're not, say, in a dairy or another manure and animal-based system, the soil test lab will still give you a recommendation. You're growing sweet corn, they know it takes, 150 pounds of nitrogen per acre for sweet corn on average, so they'll give you that number. Or if you say you use manure, they'll make it a smaller number and just get you in the ballpark.
Craig?
Yes.
Back up.
Yeah.
Again. Like your basic soil test, can you explain for Western Washington what the value is of the EC and then maybe why, because historically, and I go back to the old Wazoo test, we used to use CEC, which did seem, and also organic matter. Why you're discrediting organic matter.
What I would say, they're useful, but they're not necessary, is what I would say. And actually, in a manured system, some of these fall into that category as well. But, organic matter, there's really two things that control organic matter. One is kind of the native organic matter level of the soil. So if you're in a peat bog, you're going to be really high organic matter. If you're in a wetter soil or with more clay, you're going to be higher in organic matter. And then the second is management. Have we managed the soil in a way that's going to deplete it, add, or maintain? And so those pieces are together. So one thing is if you had a long history of organic matter in your soil, you could see whether you're going uphill or downhill. So that would be an advantage to it. As a snapshot, not much use. As a long term, that would be of some use.
Well then, what value does the EC in Western Washington, under most conditions,
I don't
provide?
I don't see any value to it.
Great.
Yes.
On the new sampling requirements, organic matter and ammonia are both on that for the state.
Oh, okay. Organic matter, I can understand. Ammonia, there are some big problems with ammonia because ammonia is not all that stable in the soil samples, and shortly after a manure application, the ammonia numbers tell you something. But you go much beyond that, and they're not really telling us anything. They can bounce around all over the place, and and that's been one of Dan Sullivan's mantras for quite a while. So basing anything on ammonia testing makes me nervous.
Are you going to talk about the conversion factor to pounds per acre?
I wasn't, but I can.
So the organic matter is one way we have looked at that, at the bulk density.
Okay.
Comparing that.
Okay, sure. So that would be a way to go. When I get to those tests, remind me of that.
I still wonder, would the CEC, could that be valuable for maybe predicting leaching potential?
It would, but to me it's a whole lot simpler to just hand texture your soil. If you have a sandy soil, your CEC, which is the ability to hold on to ions, is going to be fairly low. If you have more clay in your soil and more organic matter, that's where there's all the surfaces and the charges that can hold on to those nutrients. So CEC, it's useful, but there's other ways that we can get at it. I guess if you have to have organic matter and you have to have maybe something else that you're required to have, then you could just pay for the whole set of options and get the whole 9 yards test. And it's not that much more expensive. Now, in interpreting soil tests, and I'll show an example of actually a sheet in a minute, but it's pretty simple. Nutrient status low, medium, high. Sometimes you'll see excess. Low, it's like on that little graph we showed with the phosphorus. Fertilizer response is likely. Okay, so if we're in a system where you're using fertilizers, you're going to get your money's worth, very likely. Medium, Sometimes a fertilizer response, sometimes not. Good insurance policy. And they will recommend a lower rate of the nutrients. And high, you're probably throwing your money away. Excessive, that doesn't necessarily mean that you're in for trouble. It just means that there's absolutely no sense in adding more of that particular nutrient. So here's a soil test sheet. This is from one lab. There's different labs with different sheets, and I stole this from Doug Collins, who was a colleague who was much younger and much more tech savvy than me. So what he did was he created all this stuff so we could home in on, okay, here's organic matter. And this test is the whole 9 yards test. And it's 6.8%. That's a lot of organic matter in a soil. This is one that is probably in a wetter landscape position, maybe been in grass for a long time, maybe had a lot of manure applied to it. This one does have a nitrate test. I'm going to defer on talking about this one for a few minutes here. For non-manured systems, the nitrate test is not very useful. It has a phosphorus test. This is an important one to us. There's 2 phosphorus tests. There's the weak Bray, and that's that acid fluoride test that we use west of the mountains. It is the best calibrator for us. East of the mountains, they use this sodium bicarbonate test. This lab runs them both, but since this was a west side sample, they just gave the results here. And notice this test result is 46 parts per million. For any of these numbers, except for the nitrogen, we don't make a direct calibration from parts per million to pounds per acre. Okay, these are just indices. Any lab that claims that that's related to some number of pounds per acre, I would probably start looking for another lab. Okay, and you do see some that do that. But here's the low, medium, and high. 46 parts per million Bray is high. And so that says that we have adequate phosphorus to meet our nutrient needs. If we're in a system with a history of manure, we see a lot of triple-digit Bray phosphorus. It just says we've got plenty of phosphorus in our soils. Potassium, this one's in the medium potassium range. In manured soils, a lot of times we'll get up into the high end of the range. This one has adequate magnesium, a little bit low on calcium. Guess what? We're going to see some lime recommended for that. Sodium, you don't see much sodium in our soils because it leaches out very readily. Okay, this does show the base saturation part, and I'm not going to get into that. That's not that important, really. What I do want to show is this one. We have our pH. I just have a little box here, and they show whether, kind of a little bar. Okay, we're moderately acid soil there. And then they have this buffer pH number here. And this number, that is what they're going to use to determine how much lime this soil might need. So you get a soil test result back and you see a buffer pH. That's the recommendation. What they're going to use is the recommendation for the lime requirement, which we're going to find down at the bottom here. And they have all their nutrient recommendations down here. And so they're recommending 9,000 pounds of lime per acre, which is 4.5 tons. So if this were a pasture, we'd ignore that and just add 2 tons of lime. And we're probably, pH 5.5 for a pasture, we're about borderline there. They probably would have recommended less. I don't know what crop this was for, but if it was a pasture, they would have recommended less for that. So that's how we interpret this. Are there any questions on this? And I know everyone has a different, different type of, different lab you may go to. The tests may look a little bit different, but a lot of them have gone to these little bar graphs in the high, medium, low, as well as giving you the numbers, and then some fertilizer recommendation with it. Okay, here's my electrical conductivity slide. Not traditionally done for soils west of the Cascades. Why not? Because it's a measure of salts, and salts leach out in our environment. And I understand this is a requirement now, which it's going to be useful in Yakima. I could make my little thing useful in Yakima, waste in Whatcom, if we want to say. But that's what it is. Any questions on that? Now, we use the soil test results along with fertilizer guides, and I mentioned that, whether it's a pasture management bulletin, a corn bulletin, or whatever, to determine how much fertilizer to use. But when we are looking at a situation with repeated applications of manure, in some cases the soil tests we're using a little bit differently. One is in manured fields. We're going to expect higher levels of organic matter. Why? Because we've been adding organic materials over the years. That's a good thing for the soil. It's going to increase our nitrogen supply in the soil. And this is not just available nitrogen, but that's slow release nitrogen. So we're going to have a bigger bank in the soil. And that's something that we don't measure by soil testing, because we don't have a simple test to do that. And we're going to have higher levels of phosphorus and potassium, because generally manure contains more phosphorus than the plants need when we add enough nitrogen. And the manure also contains a lot of potassium, so we tend to see those build up over time. So before I get to the soil nitrogen test, we just have to do our one quiz today. Since I'm an extension guy, I always have to have one of these quizzes. So what are the three most common forms of nitrogen in soils and soil amendments? What's this one up on the top here? The most abundant form of nitrogen.
TKN. Organic.
Yes, it'd be organic, the organic nitrogen. That's right. And what is organic nitrogen? What is it first? What do the bugs first decompose it into or release from it as they break it down? That first waste product. So that's ammonium. And then in the presence of oxygen, that ammonium is converted to what? Nitrate. And which of these are available to plants? So the ammonium and the nitrate, these two are available to plants. And the nitrate, if we have too much, that's the one that can potentially get us into trouble. So nitrate is transient in soil. We're relying on the soil organisms to release it. The plants are taking it up, and it leaches in the wintertime. But what we've learned is there's a couple points in time where we can take nitrate snapshots and we can learn something about the nitrogen status of the soil, and it can help us with management. One of them is called the pre-sidedress nitrate test. This is done, about when the corn is 6 to 12 inches tall, and a lot of research has shown there's a correlation in manured systems where we're growing corn between the nitrate level in the soil at this time and whether the corn would respond to any further nitrogen application. And so this is pretty widely known, and there's a publication that I was one of the junior authors on back about 15 years ago, and it's still a valid publication. We did some work up here in Whatcom County evaluating the pre-sidedress nitrate test, and we had a number, you probably remember this, when we were hauling corn out of these plots all over the county, and what we found was that we kind of modified the pre-sidedress nitrate test. As if your field had a manure history, you did not need to add any more nitrogen. If your field did not have a manure history, it was worthwhile taking the pre-sidedress nitrate test to see what else you needed. Now, I'm not saying that that's going to work everywhere, but we found that the manure history just about guaranteed there would be adequate nitrogen in that soil. It would have a high pre-sidedress nitrate test, and when we compared fertilized to unfertilized plots, there was no difference. And I think one good outcome of that is, again, for folks who can remember a while back, if you go back in the 80s, a lot of dairy farmers were adding nitrogen fertilizer as well as manure to their soils. And I think you see very little nitrogen fertilizer at this point because the manure is doing all we need and then some. The second test is the post-harvest nitrate test. We used to call this the report card test. And the idea behind this is to see how much nitrogen is left in the soil at the end of the season. I'll remember that conversion factor here because it comes into play. And then that's used. We can use it to modify management in the future. It's measuring the past. And we generally do this in the fall. This is at the time where crop uptake is slowed down. In the case of corn, the crop uptake is quit by this point, but before the leaching season has started, so we can look at the potential for leaching. And we found that generally just sampling the top foot of soil is adequate. And again, if you're hiring someone to take the sample, they're going to know about the sample preservation. You either get them to the lab cold, or you air dry them right away and get them to the lab that way, and the nitrate will be stable in those situations. The question that came up earlier was that this is a test that we take parts per million and we convert to pounds per acre. There's a direct correlation here. We're looking at what's hanging out there in the soil, and we can say, well, this is so many pounds per acre of nitrogen. And if you have, and right now I'm not remembering the numbers in this bulletin, although I was the co-author on this one. My memory is weak. I didn't bring it with me, so I don't remember the exact numbers in there. But the results come back in parts per million. To convert it to pounds per acre, we need to know how many pounds does an acre of soil, a foot deep, weigh. And that's going to vary. If you have a lot of organic matter in your soil, a lot of volcanic ash in your soil, an acre of soil might weigh 2.5 million pounds. That would be at the low end, at the real low end. If you don't have so much organic matter in it, it might weigh 3.5 million pounds. And so the conversion factor that you use kind of depends on the density of your soil. And so there's always this temptation, well, I'm right on the borderline of getting into trouble. And if my soil were just a little, if I multiplied it by 2.8 instead of 3.2, I'm the other side of the line. So the kind of where the organic matter comes in, if you're high organic matter, if you're up around 5% organic matter, certainly that lower number makes more sense. You can look on the soil survey. If you're a high volcanic ash soil, that lower number is going to make more sense. We've actually measured a bunch of bulk densities around, and they kind of fall into a range that's between that 1.5 to 3.5 million pounds per acre of soil. And I don't know if that answers your question or anything else you were looking for me to bring up on that.
You brought it up. The number 15 parts per million, and I was wondering if the pounds per acre is what it went to 55, which would be 3.5.
Yeah.
And you explained it well, but we do have a lot of peat fields that are down in the 1 million pounds per acre.
Right, they'll be down that low, that's right.
So there is a big difference in that, and we have had organic matters build up 10% on a mineral soil, so there is a big...
Right, absolutely, there is a big difference there. And
the soil survey does give a bulk density.
Yeah.
So you
could kind of ballpark it. You know whether you're going to tend to run lower or high. Boy, there was something you said that triggered my mind, and now I've forgotten what it was about bulk density or the parts per million numbers. Yeah, I'm not remembering exactly right now what it was, but yeah, that 55 would be based on the 3.5. Yeah, Dan was the originator of this, and then we went through a kind of a modification back just before this bulletin came out, and that's been about 10 years now. Yeah, exactly 10 years since that came out. Okay, I'll talk a little bit about phosphorus. We hear kind of growing issues with phosphorus, and the question is why the concern about it. Phosphorus is a plant nutrient. It's not toxic. It's not reactive in any kind of way. So why are we concerned about phosphorus? Okay, and this is my poster child photo that was supplied by the Snohomish County Conservation District. And the reason is that it's predominantly a freshwater issue, okay, lakes and streams. Too much phosphorus, you get eutrophication, and eutrophication is Greek for too much of a good thing. Okay, I'm lying about that, but that's the way we can think about it. It's an excess supply of nutrients, and what happens in lakes, which are traditionally phosphorus deficient, that's the nutrient that kind of is at the lowest level, at least as far as the plants are concerned. You add phosphorus and you start growing algae and other aquatic plants. And so you get this kind of green scum on the surface. And if you're going to go swimming, I don't know. If you're going to go fishing, I don't know. And then this algae dies. And when it dies, it becomes what we call biological oxygen demand. It acts about the same way as if you put sewage in the lake. Okay, and it goes anaerobic because the microbes are trying to break this stuff down, and so it's no longer good fishing water quality, it's no longer good drinking water quality. It so happens that Chesapeake Bay, which is kind of the East Coast Puget Sound, although it's not entirely, it's a kind of a brackish water body, it is phosphorus sensitive, and there's a lot of phosphorus inputs around the bay, and Washington, D.C. sits very close to the Chesapeake Bay, so phosphorus became a kind of a big national deal. Here in Whatcom County, it's a big deal in Lake Whatcom. Fortunately, there's not a whole lot of agriculture going on around Lake Whatcom, but I just point this out that phosphorus is another nutrient that we're concerned about. And manure has lots of phosphorus in it. One bit of good news is if we look at soil testing, is this curve on the top here. This is our yield curve, and it says, we get up to about this point somewhere, and we don't need to add any more phosphorus fertilizer to improve our yields. So if we're paying money out of our pocket to buy that phosphorus fertilizer, our soil test gets up to there, we would quit. What this is saying here, this is kind of the risk of loss environmentally, is we don't get into trouble until some point quite a bit higher soil test phosphorus. There's a bit of there's a buffer ground in there. And so when we're using manure, we hit this optimum here. We'll hit that pretty darn quick. It doesn't mean that we suddenly can't use manure anymore, because there's still quite a range into where we start getting the potential for phosphorus loss. And then there's another piece beyond that, which is the phosphorus index. And I'll just describe this, because this is an NRCS assessment tool where we can estimate the potential risk for phosphorus loss. And so it takes into account our soil test phosphorus. That's one piece of it. It takes into account our amendment. How much are we adding, when are we adding, and how much phosphorus in it. It takes into account risk of surface runoff, even risk of subsurface runoff. That could be, if you hit a hard pan and go along the hard pan, and even potential risk of leaching, and those subsurface things we would not expect in our environment very much, and then erosion loss as well. And then you put all those things together, and you come up with a phosphorus index. And where we have the potential for phosphorus problems is where we have a high P source, soil with a high soil test, and we're still adding manure to it, and risk of high P transport, whether it's runoff, erosion, etc. And that is where we have high potential for transport to water. Then the other piece you need is the water there to transport it to, where you're draining into a phosphorus-sensitive body of water. And when you have all those criteria is when we have phosphorus problems. So just to kind of review, the source factors, the soil test phosphorus level is just one piece. The amendment rate and application method is another piece. Transport factors, what's the risk of erosion? And again, these are things that NRCS figures out for us. Is there erosion potential from irrigation? What's our runoff class? How far are we to our surface waters? What kind of widths of buffers do we have to those surface waters? Do we have subsurface drainage? Do we have flooding risks in here? One thing that we know with phosphorus, it is not highly soluble in water. So generally phosphorus does not leach into groundwater. So phosphorus is not a groundwater problem. The only place where I'm really aware that it is this is back on the East Coast, not far from Chesapeake Bay, where they have some soils that are basically piles of sand. Very little capacity to bind much of anything. And they've applied chicken manure for who knows how many decades, and they've actually now have phosphorus moving through that soil into the shallow groundwater, and then it gets out into the bay where it starts causing problems.
What about tiled fields?
So tiled fields, that would be where that subsurface drainage would come. Not that much movement, in the tiled fields. I would expect maybe a little more than in untiled fields. You can get some preferential flow, but again, the low phosphorus solubility helps us. Erosion, particulate is a problem. Runoff of the surface, you can get some dissolution in the surface water, but phosphorus in contact with soil, usually the soil wins. It's got a large capacity to fix phosphorus.
Then, it would seem, from what I'm hearing, it would be the p-index or the soil phosphorus levels at the margins of a field or a water course would be more significant than what would be on the inside of the field, some distance away from a water course?
Yeah, I guess if we were to look at, say, soil test, that would be true, but we would still look at kind of what's across the field, as that's what's kind of back upstream, potentially waiting in line. So a phosphorus index you would do on a whole field, or you might do it, on fields on a whole farm and see what you have. From a research point of view, it might be interesting to look at a phosphorus transect, and what you might find is that, let's say at the edge of the field, in a buffer where you're not applying anything, that your phosphorus is low, and in 15 feet away it's high, and there's not been that much movement from the low to the high, and that would be a very good news situation.
I guess where I'm going with this is again, are they painting too broad a brush with the tool? And if we're thinking of mitigation strategies, binding amendments that we would perhaps broadcast on the margins of fields to reduce the transport of the...
Okay, what we do know is if you have high phosphorus soils, you can add something like alum, which is an aluminum-based compound, and what the alum is doing is it's binding phosphorus just like the soil does, except we've concentrated that aluminum. Now, it's not in a plant-available form. After I told us, we'd all be dead if that aluminum was available. But it is able to bind up the phosphorus. So there are areas of the country where phosphorus is a big issue, where they're actually doing that in fields. And what I don't know, because that's a really intriguing idea, is can you do it simply around the buffers, and so you don't have to apply to the whole field, and have an effective phosphorus removal mechanism.
Or you would just perhaps not manure so close that you would have a manure
right.
setback. And thinking, I know wastewater treatment plants have residuals.
Yep.
They're interested in having them available, and so
right.
given the environmental concern, thinking of mitigation strategies.
Right.
How do we really tailor it? Because the implication of the soil test across a big field without the potential of much of it transport seems problematic for a livestock operation.
And I think that's part of where the phosphorus index comes in, is it takes into account those transport factors. But I think then, the fine-tuning can be very valuable to us, and it would be interesting, if phosphorus rears its head to the point where, there's a lot of action that's demanded, is what is the research saying about those alum applications? Can we do it around the borders of fields? That's something I hadn't thought of, but that's an intriguing idea.
It really depresses the pH too, doesn't it?
It's going to tend to do that, but I know in the southeast there's quite a bit of that going on.
Because I thought that's one of the things you use, say, with rhododendrons. If you
Right.
Other plants, they say, don't put too much on.
Yeah.
Because, but it is used to, for chlorosis and rhododendrons
Yeah.
and so forth.
Yeah. So that's one potential approach. Again, we're gonna have to wait and see. I think a great irony about phosphorus is if you read about kind of resources in the future, phosphorus is the first nutrient we're going to run out of. We're not discovering new phosphorus sources, and we're utilizing the others. And where we have intensive animal agriculture, we are accumulating phosphorus. We're becoming kind of the phosphorus mines of the future. I guess the good news is when phosphorus is short, we won't be short. For 100 years, and then the problems will start coming. But yeah, that's one of the ironies about phosphorus. And this is I don't know how long I've talked here. I think my watch stopped.
Yeah, about 10 more minutes.
Oh, okay, and because I'm just about to go. This might be the last slide right here. So this is just my cartoon of the p-index calculations. You take your source factors, and each one has a specific score and a specific weight of the value depending on different situations. You take so we have our soil source, we have our amendment source. You take all these transport factors, and there's a way that a number comes out of this, and you add them together on the west side, and you come up with a phosphorus index. And what it does is it gives a handle. Do I have a situation where I have a high risk, a low risk? Do I need to start thinking about phosphorus or not? And then beyond that, you ask the other questions: is our watershed draining into any phosphorus-sensitive waters or not? Because that has to be part of the issue as well. And that should, and that's it.